Risk estimates must be combined in a way that is technically correct so that the collective impact of all the potential failure modes can be expressed in a credible manner. We need to be careful not to incorrectly inflate the total risk by how we combine these failure modes to get a total. When breach characteristics and consequences are different, we need to be very careful not to distort the estimated risk by how we combine them. If you can think back to a few slides ago, we discussed how branches must be mutually exclusive. Failure modes are often not mutually exclusive. So how do we deal with where failure modes overlap or intersect? There are three options that we can use to deal with the issue. The first option is to simply ignore the intersection events and assume failure modes are mutually exclusive. If we do this, we will overestimate the result by some amount, but that is fine so long as the intersection probability is small and the consequences are not significantly different for the intersecting event. Option 2 is we can ignore the intersection events but distribute the probability. In doing so, you will get the correct total probability of failure, but the risk will not be quite right because you've not considered the potential for increased consequences that may result from the intersecting event. This is an acceptable approach so long as the consequences are not significantly different from the intersecting event, which is typically the case. The third and final option is to just go for it and to enumerate the intersection event. You will get the same probability of failure as you would from option 2, but will have a more precise representation of the risk because you are explicitly considering all the possible breach combinations. This slide gives a visual of the three methods that I just discussed, where we can ignore, distribute, or enumerate the intersection. Each of these methods provides ways to go from statistically independent failure modes to mutually exclusive failure modes, but none are without limitations or drawbacks. In the bottom left of the figure, you can clearly see how ignoring the intersection overestimates the risk because the intersection probability is double counted. In the other two methods, you can see how the area is the same for both, and it will get the same total probability of failure. The issue with distributing the intersection is we do not consider the consequences of the intersection, but evaluating that extra scenario can be a lot of work for a scenario that has little contribution to the total risk. So the vast majority of the time, we will simply distribute the intersection. This is where we can consider the unimodal bounds theorem to bound the problem. The theorem states that the total probability of failure is somewhere between the highest single failure mode probability and the total probability of failure of the system calculated using De Morgan's rule. If the total probability is equal to the probability of the highest single failure mode, then the potential failure modes are perfectly correlated. If the total probability is equal to the probability calculated by De Morgan's rule, then the failure modes are perfectly uncorrelated or independent. The true solution will be somewhere in between these values. When one PFM has a dominant probability, one that is much higher than that of the other failure modes, the difference between the unimodal bounds will be quite small, which I will illustrate next with an example. In this example, we are given three system response probabilities from three different overtopping failure modes. The unimodal bounds theorem states the total probability will be somewhere in between the highest individual failure mode probability, which will be overtopping of the saddle dam, P3, and 1 minus the products of the event's complements, or De Morgan's rule. So we take 1 minus P1, 1 minus P2, and 1 minus P3, multiply them together, and subtract that product from 1 to calculate the upper bound of the total failure probability. From this example, you can see that the probability will be somewhere between 0.5 and 0.55. The difference is small because P3 is so much larger than the other potential failure modes. But if those probabilities had all been similar, the spread between the bounds would increase. Here's a quick overview of the 5 models that will be covered. There is a marginal risk model, the exclusive risk model, the joint risk model, common cause adjustment, and the competing risk model. Of the risk models, the common cause adjustment has been the most prominent for past quantitative risk assessments. The first method is the marginal risk method, which considers only marginal probabilities. A marginal probability describes the probability of an event irrespective of the occurrence of other events. So for a set of potential failure modes, a total is not calculated when using the marginal risk model. We use this method to identify actionable potential failure modes because the risk associated with a potential failure mode can be reduced by the presence of other potential failure modes. While this model is simple and flexible, it is not typically representative of actual risk because the actual risk will typically be the result of multiple failure modes. The exclusive risk model ignores the intersection of potential failure modes and assumes the failure modes are mutually exclusive. To calculate the total using this model, the marginal probabilities are summed. Again, a marginal probability describes the probability of an event irrespective of the occurrence of other events. The exclusive risk model is appropriate when the dependence among potential failure modes is negligible with respect to both probability and consequences. This method is often used to simplify risk calculations when completing a screening. The joint risk model enumerates all possible combinations, which are then summed together to calculate the total probability. This is necessary when joint failure can influence the risk estimate, such as for a long levee where multiple breaches can occur during the same flood event. While this model will produce the most accurate result, it can be very cumbersome when there are more than a couple failure modes. Assumptions can be made to simplify the effort, but the consequences for each of the joint failure events must be evaluated. For example, when there are 3 potential failure modes, 7 unique failure events must be evaluated. How to calculate the probability of each of these events is shown to the right. These probabilities can then be summed to get the total probability, the same total probability that would be calculated using De Morgan's rule. The next risk model is the common cause adjustment. This method distributes the intersection to avoid overestimation of the total probability. The intersection is weighted and distributed by potential failure mode, as shown by the equation on the screen, with the largest failure mode getting the largest portion of the intersection, and the smallest potential failure mode getting the smallest portion. First, the total probability is calculated using De Morgan's rule. That probability is multiplied by the probability of the given failure mode, then divided by the sum of all potential failure modes. So what kind of failure mode should we consider a common cause adjustment? We would consider common cause adjustment for failure modes that can occur simultaneously at a single section due to a single initiating event, such as concentrated leak erosion along a conduit and backward erosion piping beneath the same conduit. We would also consider an adjustment for the potential failure modes that can occur simultaneously in multiple sections due to a single initiating event. In these instances, the total probability of failure is some combination of the probabilities of failure that are associated with each of the possible modes. This adjustment should be made simultaneously over all sections of a multi-section dam in all common cause failure modes for all sections. It should be calculated and applied separately in each probability interval for a loading type. Now let's take a look at how to perform a common cause adjustment at a given stage. We are given probabilities for 3 potential failure modes, P1, P2, and P3. For P1, which has a probability of 0.65, we are going to take that 0.65 probability and multiply it by the De Morgan's rule equation, which is equal to 1 minus the product of all the failure mode probability complements. Then we are going to divide by the sum of all the failure mode probabilities. This reduces the probability from 0.65 to 0.445. When you make an adjustment, the adjusted probability will always decrease. It will never increase. We then repeat the process for the other 2 failure modes. In this example, if I had ignored the intersection and simply summed the probabilities, I would get a probability greater than 1, which violates the rules because all probabilities must be greater than or equal to 0 and less than or equal to 1. When I perform De Morgan's rule and distribute the intersection, I now get the correct probability and a probability that is less than 1. Here's one more example covering common cause adjustment, after which I'll ask you to try an exercise on your own. We start with the marginal system response in the first table. In the second table, we will take the complement of each probability as an intermediate step to help us in the next step when we apply De Morgan's rule. This step is not really part of De Morgan's rule, but it'll make life easier when using Microsoft Excel because we'll be set up to use a product function, which I'll show you shortly. The adjusted probabilities are shown in the final table. For failure mode D at a stage of elevation 475, I'll take 1 minus the product of all the complements, which are the values in the green box. I'll divide that by the sum of all the marginal probabilities in the red box, and then multiply by the individual marginal probability, which is in the blue box. The result will be the adjusted value in the gold box. When one failure mode has a dominant probability, or when all the probabilities are relatively small, the common cause adjustment will usually be small. We then repeat the process for every stage in failure mode. To get the adjusted probability of PFM-B at a stage of elevation 525, the rows and values we use for the calculation will shift downward, but the procedure is exactly the same. The final risk model covered in this module is the competing risk model, which is analogous to a weakest link approach. The model assumes joint failures cannot occur, such that the first failure precludes additional failures and/or additional consequences. As such, the total risk is calculated for each potential failure mode, assuming failure does not occur by any of the other modes, because there is no intersection of failure events. One example of where the competing risk model is appropriate is a levee breaching prior to overtopping and filling the levied area, thereby preventing another breach and additional consequences from occurring when the levee later overtops. Another would be a dam breach that quickly empties the reservoir, thereby preventing breach by any other potential failure mode. In the competing risk model, there is a one-to-one correspondence between the set of potential failure modes and the set of possible failure events. For example, a system with 3 potential failure modes, A, B, and C, there are 3 mutually exclusive failure events, A but not B or C, B but not A or C, and C but not A or B. The response for each potential failure mode is calculated assuming the survival of the remaining potential failure modes up to the specified hazard. The adjusted system response A from the competing risk model is equal to the integral of the system response for A multiplied by the survival function for the remaining failure modes with respect to the hazard. The survival function will be the product of the system response complements of the other failure modes. In this example, for A but not B or C, the survival function will be 1 minus the system response of failure mode B multiplied by 1 minus failure mode C. So, in the competing risk model, the probability for A becomes the integral of the system response for A multiplied by the probability B does not occur multiplied by the probability C does not occur. The probability for B becomes the integral of the system response for B multiplied by the probability A does not occur multiplied by the probability C does not occur. And the probability of C becomes the integral of the system response for C multiplied by the probability A does not occur multiplied by the probability B does not occur. An integral of a function is equal to a numerical value equal to the area under the graph of that function. In the case of failure mode A within the competing risk model, the function is the system response of A multiplied by the survival function of the other failure modes, 1 minus the system response probability of B, times 1 minus the system response probability of C. We can get the solution for the integral by plotting the system response for A against the survival function of the other failure modes and calculating the area beneath the curve. Please note that the system response and the survival function are all a function of the hazard Q. The system response for all failure modes will be taken to be 0 for hazard Q0. This means at Q0, the system response for A will be equal to 0 and the survival function will be equal to 1 at Q0. So for hazard Q1, we are going to integrate from Q0 to Q1. The system response for A, assuming competing risk, will be equal to the area shown in red. The area can be calculated by taking the change in system response A and multiplying it by 1/2 times the sum of the survival function at Q0 and at Q1. For Q2, we will integrate from Q0 to Q2, and the area now becomes the area of the first trapezoid from the prior slide plus the area of the next trapezoid. So we take the probability we calculated at Q1, 0.008, and add to it the area of the next trapezoid. And then for Q3, integrating from Q0 to Q3, we take the entire area we calculated for Q2 and add the area of the next trapezoid. This process continues until the full range of the hazard has been evaluated. In the prior slides, to solve the integral, we calculated the area under the curve, and we did so by using the trapezoidal rule, which divides the total area into trapezoids. Using the trapezoidal rule, the integrals can be expressed by the relationship shown here at the bottom of the slide. This is the same relationship that we used in the prior slides to calculate the area under the curve and solve the integral. This brings us to an example. We are given the system response for 4 potential failure modes, A, B, C, and D, and we are going to calculate their adjusted system response probabilities, assuming competing risk. The top table is the marginal system response probabilities. The second table is the complement of each system response, or 1 minus the system response. Calculating the complement up front will simplify the final equation, kind of like it did when we were performing a common cause adjustment. Finally, the third table is the solution to the example. Let's step through the process for failure mode D. To get the adjusted system response for failure mode D, assuming competing risk, we start by subtracting the system response for failure mode D at Q0 from the system response for failure mode D at Q1, as shown in the red box. Remember that the system response for all the failure modes will be equal to 0 for hazard Q0. Next, we are going to calculate the survival function for both Q1 and Q0 and add them together. At Q1, the survival function is equal to the complement of the system response of A times the complement of the system response of B times the complement of the system response of C, as shown in the green box. At Q0, the system response for A, B, and C are all equal to 0, and the survival function is 1 minus 0 times 1 minus 0 times 1 minus 0, as shown in the blue box. Putting the pieces together using the equation from the prior slide, we get the system response for failure mode D at Q1 minus 0 times 0.5 times the quantity of the survival function of the other failure modes at Q1 plus the survival function at Q0 to get a probability of 6.74 times 10 to the minus 2. For Q2, we follow the same procedure, but everything shifts down a row. We will take the system response for failure mode D at Q2 minus the system response for failure mode D at Q1, as shown in the red box, times 0.5 times the quantity of the survival function of the other failure modes at Q2 in the green box, plus the survival function at Q1 in the blue box. We add to that the adjusted probability for failure mode D at Q1 because we want the entire area under the curve from Q0 to Q2, not just from Q1 to Q2. This results in a probability of 7.02 times 10 to the minus 2. We then repeat the same procedure for Q3. The inputs again just shift down a row. And then again, the same thing for Q4 and on down until we have calculated probabilities for each hazard in the table. For the other failure modes, the process is the same. The equation on this slide is for failure mode A at Q3. This time, the survival function will be defined by the complements of failure modes B, C, and D. While in most cases the total risk will not differ much with the risk model used, the preferred risk model depends on the tools available and the level of accuracy required. If powerful software is available to perform the risk calculations, such as RMC total risk, the joint risk model will be the most accurate and is recommended. Simplifying assumptions can be made to estimate the consequences for the joint failure events, such as taking the maximum of the consequences between the failure modes, summing them together, or taking the average. If calculations are being done by spreadsheet and there are more than 2 or 3 failure modes, the competing risk model is recommended. Use of competing risk is relatively new for dam and levee safety risk assessments and is used in the current version of the Corps Levee Screening Tool, LST 2.0. Common cause adjustment was the risk model most often used in quantitative risk assessments, but it has since fallen out of favor because competing risk is more accurate and better represents the characteristics of most dams and levees. Keep in mind the accuracy of the estimate when using the competing risk model will be dependent on the number of failure modes and the number of intervals used to approximate the integrals using the trapezoidal rule. Depending on the spreadsheet, this may be a limiting factor. For screenings, or when dependence among potential failure modes is negligible with respect to both probability and consequences, the exclusive risk model can be used.